been talking about evaluating limits analytically. Yesterday we looked at like kind of the cancellation method. I mean, I don't know what you call it, but it's just factoring and canceling the offending factors. We looked at that if we started off with a rational function or if we started off with a complex fraction, fractions on the top and the bottom. Remember, in that case, I don't have an example from yesterday, but just describe to me what was the most efficient way to do that. If I had fractions in the top and fractions in the bottom, what was the most efficient way to resolve the indeterminacy? Clear the fractions. Good. Multiply the top and the bottom by the LCD of all fractions, right? On the top and bottom. And that'll clear all the fractions. Good. Okay, so today we're going to look at another case. This is called the rationalizing technique. What happens if you have a limit involving radicals that's indeterminate? Okay, so if we try to evaluate this one directly, what do we get?
0 over 0.
0 over 0. So it's indeterminate, right? So ultimately, can you tell me what factors are going to have to cancel?
The x's.
X's, right? Because the 0 of the factor x is 0, isn't it? Right. Okay. So we know that as x approaches 0, the factor x is the one that's going to go to 0. And so that ultimately is going to have to cancel from the top and the bottom. So we can already anticipate that, which is very helpful. Okay, so what did I have here? Oh, I know. Okay, so what are we going to, I'm outsmarting myself there. Okay, so what am I going to have to do, do you think, to somehow deal with this indeterminacy? What am I going to multiply top and the bottom by? If I just multiply top and bottom by x, it doesn't really accomplish anything.
X squared.
Nope, still not going to
1 over
accomplish
1.
See, okay, something like that. Now think about the problem here. The problem is, on the top, we have to somehow subtly introduce a factor of x. But the problem we have here is that this expression that goes to 0 on the top involves a radical, right? Involves a square root. So let's think about this. Let's be problem solvers here, and let's think about this now. One of the issues here is that we've got square roots involved. What we would really like to do is manufacture a way to make the expression that involves a radical not equal to 0. Right now it is equal to 0, right? If x goes to 0, I get the square root of 1 minus 1, which is 0. So how could I somehow have to get rid of that radical that's involved in the factor that's indeterminate, that goes to 0? Suggestions. Okay, so that's not a bad suggestion. If we could, like the idea of squaring something to get rid of a radical. However, squaring something is not a legitimate algebra step. I'll give you an example because it's going to change the values of things. Like if we were doing a problem, like if I had something like what can I think about? Something like 2x equals x plus 1. Okay. So if I square both sides, the problem is, I'm not going to try to think, well, yeah, I don't want to have to come up with an example of that. It's going to take too long. I know how I could do it, but the problem with that is if you square both sides, remember this from a couple of years ago, when you take both sides of an equation to a power, you introduce the possibility of what? Say it again? Okay, well, kind of false solutions, extraneous solutions, right? So for that reason, we don't really want to square things, right? That makes sense. And also, squaring the top and bottom of a fraction, like if I had, for example, the fraction 2 over 3, if I square the top and the bottom, I'm going to get 4/9, which is a different value, right? Make sense? Okay, so that's not going to be an option for us. What else, though? It was the right idea. I multiply the top and the bottom, you might think multiplying the top and the bottom by the square, by the expression that's on the top, maybe, right? That's a reasonable thing to maybe try. A lot of times that's a suggestion. What if I multiply top and bottom by that? Square root of x plus 1 minus 1. However, that doesn't really help us very much because I'm still going to end up with something on the top that involves square roots. Like if I did that, if I FOILed this out, I'm going to get, on the top, I'm going to get, oh no, is it doing this thing? I'm about ready to just kick my technology here.
Go back to the old.
Okay, so if I were to multiply top and bottom by that, I'm going to cheat and just copy and paste a little bit here. So let's see if I do.
Oh, what if you make two separate fractions?
Oh my gosh.
No, because we did that like plus one.
So if I did this and I FOILed this out, what am I going to get? Well, on the top, I'm going to get an x plus 1. I'm going to get a minus that radical, another minus that radical, so negative minus 2 times the square root of x plus 1 plus 1. Right? And if I let x go to 0 there, that's still going to, that whole expression is going to go to 0. Right? I'm going to get 2 minus 2. Still goes to 0, and I've still got that radical there, so it didn't do any good.
I want to go down to breaking the club. Like, I feel like it's going to do much, but I want to try.
Okay, there's something. I still kind of want to see if everybody, if you guys will get this here.
It's like a letter.
What could I do? Is there something I could multiply the top by and completely do away with the radicals?
0.
No?
What if you separate the fraction out? Like, what if you make it the radical x plus 1 over x minus 1 over x?
Doesn't really change anything meaningful. I'll remind you about something, though. What is, if I have a sum of two terms and I multiply that by its conjugate, what's the result?
A squared plus b squared.
A squared
Minus b.
minus b squared. Look at that, both terms are being squared. There's two terms and they're both being squared. That's what we want, isn't it? We want to get rid of the radical. What are the two terms? My a is the square root of x plus 1, and my b is 1, right? So I could multiply that by the conjugate of the numerator, which is the problematic expression. That's the one that's going to 0 that involves a radical. See, that's a great strategy. Like, look what happens if we do that. If we multiply by the conjugate of the top, this is called the rationalizing technique. And it's great because now what happens to our limit? If we expand this out, we get the limit of what on the top? Well, a minus b times a plus b, you told me, is just a squared minus b squared, right? So that's going to give me, what is the square root of x plus 1 squared? X plus 1. Minus 1 squared. Hey, look at that. On the bottom, we've just got this big mess. We just have x times the square root of x plus 1 plus 1. And you might be thinking, okay, Mr. Ryan, dummy, we got back another expression with a radical in it. What did we buy? What's different about that? It doesn't go to 0, right? If I take the limit, the square root of x plus 1 doesn't disappear. It doesn't go to 0. So we bought something important there, right? We exchanged an expression with a radical that went to 0 in the limit, which was a problem, for one which did not. Okay? And so if we simplify this, on the top, we just get the limit of x plus 1 minus 1 is just x, right? The limit of x over x times the quantity, square root of x plus 1 plus 1. You are. Okay, but what did we say had to happen? What had to cancel? You told me from the beginning. You knew the roadmap. The x's, and those cancel vertically, right? Those are factors that cancel. Now, what have we done to the graph of this thing when we cancel those x's? Well, okay, but what do we do? Like if I look at the original. Okay, well, let's look at the original function real quick. Yeah, I know I'm taking a little time on this, but I think this is pretty important. I think you will too. When it clicks, you're gonna think this is awesome. Exactly, we filled in the hole, didn't we? Yep, we filled in the hole. So if we graph the original function, right? So if we graph the function f of x equals square root of x plus 1, all divided by x. Well, okay, so if we look at the value of this function at 0, did I do that right? It's supposed to be a minus 1. No wonder that looked a little weird. There we go. If we look at the value of this thing at 0, look at that, it's undefined. There's a hole there, right? Everybody see that? Okay. Well, let's look at our new function. 1 over, we'll call this one g of x. And what's g of x? The x is canceled. So g of x is equal to 1 divided by square root of x plus 1 plus 1. Hey, what do you know? Look at those functions. They overlap perfectly. Right? If I turn off the blue one, the red one is right underneath it. But look at the blue one. It exists at 0. Right? And we can see what the answer is going to have to be. It's going to have to be 1/2, isn't it? Okay? Oops. Was the limit of 1 over square root of x plus 1 as x goes to 0. In my limit, as x goes to 0, that term disappears, and I just get 1 over the square root of 1, which is 1, plus 1. Done. Okay. What's the moral of the story? Moral of the story is if you have a function that when I take a limit, in the limit is indeterminate, and it involves a radical. The way to resolve the indeterminacy is to multiply the top and the bottom by the conjugate of the radical expression that's going to 0. Okay? And it always works. That's our rationalizing technique. Just for your notes. Okay? That's what we just kind of went through in more detail. It'll be on Google Classroom. Okay, so go try it. So I threw you guys a little curveball there, and the idea being that you don't want to always just get in the habit of you want to always think about this from a problem-solving perspective. What's the order of operations for solving these things? You're going to always try direct evaluation, and then you really only have to do a bunch of work in what case? If it's indeterminate, if it's 0 over 0, otherwise you're done, right? So this is a case where we are done. When I evaluate this directly, I just get negative 12 over the square root of 16, which is negative 3, done, right? Okay, now, go ahead and actually try that one. let's just kind of debrief, pull this together, and see if we can like distill this down to the most efficient process. So everybody was good. They tried this. They saw it was indeterminate. So we have to use our rationalizing technique. So we're going to multiply. This was good. Everybody multiplied by the conjugate of the denominator. Okay, on the top, avoid the temptation to mess this up by distributing. We don't want to do that, right? In fact, we already know if you pause and you think about, if you anticipate what has to happen, you already know that I have that factor x minus 1 that's going to have to cancel. So I got to leave it alone until I can cancel it. Right? And then what's that give me? Well, on the top, we just leave it alone. On the top, we get an ugly looking product, but it's what we want because I've got that factor x minus 1. On the bottom, this is where the magic happens. That's just a minus b times a plus b. So we get a squared, 4x plus 5 minus 9. And from there on out, it's pretty smooth sailing, right? We would just combine like terms on the bottom and factor out a 4. We'll just combine steps because you guys already went through this whole process. That's what you're going to get on the bottom, right? So there's where we cancel the indeterminacy, and now we just take our limit. Right? We let x go to 1, and this is equal to the square root of 9 plus 3 over 4, which is, did I do that wrong? 3 plus 3, oh, so that's 6 over 4. Whoops, duh. There's our limit. Yeah. Okay, good. All right. Okay, so is the limit of the rational function indeterminate? I want to backtrack just a little bit. It is, right? If I evaluate this at 3, I get, what do I get here? 9, oh, negative 3. Yeah, I get 0 over 0, don't I? Yeah, I do. Okay. Yes. Yes, it evaluates to 0 over 0, right? What factors are guaranteed to cancel to eliminate the indeterminacy? X plus 3. How come? Because it's going to be x minus negative 3, right? The 0, that makes sense? The only reason this would be indeterminate is if x equals negative 3 is a 0 of the top and the bottom. So if x equals negative 3 is a 0, x minus negative 3, x plus 3, has to be the corresponding factor. Right? So we know we're going to have x plus 3's cancel. Okay? What technique will we use to evaluate this? Factor and cancel. Yeah. So whatever we want to call that, it's kind of dorky to call it something, but we'll call it the cancellation technique. Factor the numerator, denominator, and then just cancel those factors, x plus 3's. Okay. How about this one? Is this indeterminate?
Yes.
Yes, it is. Right? I get 0 over 0. So yes, it is. What factors are guaranteed to cancel this time? X minus 7. And we know that because x is approaching 7. That really helps to know that that has to be the case. Now we just have to make that happen. So what technique would we use here? Clear fractions, and then cancel like factors, right? Good. Clear fractions by distributing 7x, agreed? That's the LCD of all the denominators. Now, if we had fractions on the top and the bottom, which is possible, I'll probably throw some of those at you for fun. Then you'd have to find the LCD of all fractions on the top and the bottom. right? Because we have to be able to cancel all the denominators, okay? So that's our cancellation technique. How about one like that? That's a little different. This looks really strange, but you're going to come to know and love this kind of expression. This is very meaningful soon. Now it doesn't mean anything. Soon that's going to be super meaningful.
I remember the X plus H.
Yeah, we did a little bit of this. Yeah.
We did it.
And I gave you a little hint. So first of all, I mean, does this evaluate to 0 or 0? It does. What do you think you would do?
I'll try to isolate X.
Right, so you know what's ultimately going to have to cancel is x's, right? Okay, well, actually, not x's, h's. Okay, there's something important going on here. What is the variable of the limit? H. Is x a variable as far as the limit is concerned? No, it acts just like a constant from the perspective of the limit, right? It's not a constant, it's a variable, but it acts like a constant from the limit's perspective. Okay? So what is going to have to cancel here again? H's. I'm going to have to get H's that cancel on the top and the bottom. I've already got one on the bottom. So now the question is, how do I get one on the top? What do I do?
Do like that whole thing instead of minus the square, you have to plus it.
Okay, so the suggestion is a conjugate. Okay? I don't need a conjugate here, though, because I don't have a radical. The conjugate was really an artifact of needing to get rid of the radical. And remember, the whole strategy behind that was a minus b times a plus b is a squared minus b squared. So the remaining terms are squared, so it extinguishes the radical, right? Because it's getting squared. We don't need that here. We don't have any radicals. We'll make this harder than it is. What do you think you're going to do here? Yeah, well, you can't distribute. Yeah, we have to expand everything out and simplify, and the math gods will take care of everything for us. They have to. They have to, because the limit is indeterminate. We have to end up with a factor h on the top that's going to cancel if we just do the math. We just have to simplify. That's all it is. Okay? So we simplify, and something must cancel. What must cancel? You already told me. The h's have to cancel. Okay? Why? Well, because h is going to 0. So let's do this. If I expand this guy out, what am I going to get? I have to use order of operations, right? I can't distribute the 8 because that quantity is being squared. So first I have to FOIL it out, so to speak. What's that going to give me? 8 times plus 8. Okay. So now what's next? Distribute the 8, so I'm going to get 8x squared plus 16x8 plus 8h squared minus 8x squared. And what happens here that's meaningful? There you go. All the naked terms go away. The ones that don't have any h's attached to them are gone. There you go. So now every remaining term has an h, so I can factor it out. There's my h, right? Okay. If I pull an h out of the remaining terms, I'm just left with what? 16x plus 8h over h. As h goes to 0, but there's my vertical cancellation. Right? And so now I just get the limit of 16x plus 8h as h goes to 0, which means that term goes away. So what's my answer? 16x. Okay, there we go.
Can you evaluate by that?
Well, no, we can't because we don't know what x is a variable. Okay, but what's important is the expression we're left with no longer has h's because we took the limit as h approached the value. Okay. Okay, so some special limits. Now this is We'll talk more about this tomorrow, but I want to just give these to you. And I'd like to prove these to you, and I probably will. Yeah, I think I will prove these to you. I'm not going to probably do it today. So the limit of sine x over x as x approaches 0, which is indeterminate, right? If I try to evaluate that directly, I get 0 over 0. The limit is equal to 1. And I'll prove that to you using an important theorem called the squeeze theorem, but not today. Here's another one that's important to us. The limit of 1 minus cosine x over x as x goes to 0, which is also indeterminate, is equal to 0. And we can get one from the other just using trig identities. But it's almost worth just remembering those two. The third one we're not going to deal with this year. Okay, so the game we're going to play now is limits involving trig functions that are indeterminate. How can we resolve the indeterminacy? Because let's take this example. The limit of tangent x over x as x goes to 0, is that indeterminate? It is, yeah, because the tangent of 0 is 0, right? How do you know that? Like, I don't really remember values of tangent, but I always do the same thing you probably do. How do you think of tangent? Yeah, so what is tangent? The ratio of sine over cosine. Right, so if you want to evaluate tangent, you just look at the ratio of sine over cosine. Well, sine of 0 is 0, cosine of 0 is 1. 0 over 1 is 0, so the tangent of 0 must be 0, right? So it is indeterminate. I got to resolve this indeterminacy. Okay, this time we're playing a little different game. This time we're not really conveniently able to coax an x out of the top because the x is the argument of a trig function. It's really difficult to get that x out in front of the trig function. So we're going to play a different game. We're going to try to use algebra and trig identities to rewrite this with one of the factors being one of our known trig limits. Okay? That's the game. Well, what do you think we should probably do when we're faced with, given the fact that our special trig limits involve sines and cosines, what should your strategy be when you involve a composite trig function, like tangent or cotangent or secant or cosecant? Write it in terms of the basic trig functions, sine and cosine, right? Okay, so then this one would just become the limit of sine x over cosine x divided by x, which is the same as x over 1, as x approaches 0. So now what? Good, so I multiply by the reciprocal of the denominator. Right. So this is equal to the limit of sine x over x cosine x as x approaches 0, right? And by the way, we could have gotten here maybe more easily. If we just changed the tangent into sine over cosine, I'm just multiplying that by 1 over x, right? Because the x is in the bottom. We could have just gone straight to that step. Okay, now what? How are we going to resolve the indeterminacy here? Is there a way I can group this that's convenient? How about this? Right? That looks familiar. Right? And so technically, remember my properties of limits. The limit of a product is equal to the product of the limits. I can separate those into two separate limits. So I could write this as the limit of sine x over x as x approaches 0 times the limit of 1 over cosine x as x approaches 0. What's the value of that limit? 1. That's our special limit, right? So that one goes to 1. If I evaluate this one directly, what is it? 1 over, what's cosine of 0? No. 1. Right? Okay, we'll get a little more of this tomorrow. Yeah.
Okay, we'll get